First, we're just going to talk a little bit about who we are and why we're on the webinar with Gurobi today. Then we'll dive deeper into an introduction to network design problems, and we'll use a sample problem to demonstrate how to use optimization for network design. After that, we'll talk about some best practices that we've learned through trial and error doing these types of projects, and then we'll have some time for Q&A at the end. Our hope through this webinar is you're going to get a little bit of both the wisdom and the knowledge of how to do this. And what I mean by that is with the knowledge, oftentimes it's things about how do I formulate a problem, the types of things you often learn in a book, you learn from doing this. And from the wisdom, we want to bring some of the tricks of the trade, some of the things that aren't written down anywhere, but are things that you develop from doing these types of projects time and time again. So even if you're, say, very familiar with MIP and they're able to formulate a problem relatively easily, we're still hoping to be able to provide some value to you with some of that wisdom. And if you're new to this, then we're hoping that, coming out of this webinar, you're going to pick up on some of the knowledge too about how to get your feet wet using optimization for these types of problems. So we're very proud to be a Gurobi Premier Partner. We're a consulting firm. We're based in Palo Alto, California, close to Stanford, although we have offices in Peru, Brazil. We have resources in Asia. We've been around for about 14 years, have done well over 1,000 projects at this point, and have over 20 PhDs on staff. The rest of our staff are master's type background for the most part from top universities. We do a lot of work across a variety of different industries, and so what we're hoping today is we'll be able to talk to you about an example of what network design looks like, but be able to have some context that we can talk about from doing network design, both in, say, consumer, retail, all the way through high tech. And then, we work across a variety of different areas, so, we'll be able to pull in, hopefully some knowledge as, questions may come up for how do you work on adjacent problems around forecasting, inventory management, promotion planning, so forth. So with that said, enough about us. Let's talk about network design. So network design is a pretty overloaded term in itself. Oftentimes it's used for, the term network design is used for a variety of different types of networks that you can build. So communication networks, computer networks, supply chain or distribution network design, road planning. If you look at humanitarian relief efforts, oftentimes those have very much a flavor of network design, as they're trying to figure out where should I pre-position or position different resources to provide maximal service. Similarly, there's many sort of emergency planning services, which emergency services planning, which also have that flavor. So for example, if I'm trying to figure out where should I put firehouses, or where should I pre-position ambulances, you get some of those types of flavors about how do I position things to provide service. And that is in part what some of these types of problems are about. Today, we're going to focus on an example from one of these types of problems, and that's going to be really on supply chain network design. That said, if you're in a different area, we think that the things we're going to talk about today are fairly scalable and are applicable across a variety of areas. So some of the things we're going to talk about are, how do you effectively engage in a project where you're working, how do you use a model, right? There's always a question of how do you formulate a model, but once you've built the model, how do you use it in a way to inform the business? And then some of the, troubleshooting issues you might get into if you're new to mixed integer programming, and how do you work around those? So even if your formulation for your particular problem, the math formulation is a little different than what we talk about today, we do hope that some of the insights we're going to talk about are going to be quite relevant to what you do. So even in the supply chain network design space, there's a lot of different flavors of that problem in itself, right? And this goes back to what I was talking about, that the term network design is a fairly overloaded term. So, sometimes people think about network design as where should I place my physical assets, right? So that can mean where do I place my distribution centers or a new distribution center if I have, a fixed production base or a fixed set of suppliers, and I know what my customers or stores, my demand points look like. You may have more than one level in there. Right here in this network below, there's 3 levels, but there's oftentimes, especially in international supply chains, multiple different levels. You might have to worry about tariffs and other types of the pragmatics about how do you move product around the globe. Sometimes, though, it's not necessarily about where do I put fixed assets, right? Sometimes it's just about I have a set of assets, how do I use them, and how do I route things more optimally, right? Perhaps my demand has changed over the past few years, and if I have a fixed set of distribution centers, I need to adjust those service areas so I can more efficiently serve the marketplace. And in all these problems, there's oftentimes issues around very particular types of business objectives you have to make sure you satisfy. So in our talk today, we're gonna kind of zoom in the focus on one of these to use it as a point to illustrate some of the challenges that we see and some of the best practices that we've learned when we're doing network design type problems. So that said, every problem I've ever worked on in this space is different. There's some differences in the formulation, right? Sometimes they're looking at fixing DCs, sometimes they're looking at how do I rationalize or increase my production base. Sometimes it's how do I distribute things. So, our hope is that what we're going to talk about today gives you that knowledge and that wisdom to be able to go and tackle your problem in whatever flavor it unfolds. So with that said, I'm going to hand it off to my colleague, Nicole, and she's going to walk us through a sample problem.
All right. Okay. All right. Russell gave a great description, as usual, of network design problems. And I'm going to introduce a sample problem. And through the sample problem, we're going to see a lot of the features that arise in some network design problems. So if you've watched webinars with me before, you know that I love a good sample problem. And up this time, we have the cookie mobsters. So the cookie mobsters are a worldwide network of mobsters who also make cookies. And as you can imagine, in this network of cookie mobsters, there are a few different levels. So it's the top level, there's something in the middle, and there's something on the bottom. And in terms of this problem, that means that we have bakeries, so they're going to bake a bunch of cookies at their bakeries, and then they're going to ship those cookies to distribution centers, where they'll either store them and keep them in inventory, maybe freeze some cookies before they hand them off to the stores where the actual demand is. So the cookie mobsters want to cut down on their costs, and they hired us to determine the lowest cost design of their cookie distribution process. So the cookie mobsters are run by two kind of top guys. The first guy is John Choclatione. He's the boss. He's in charge. He's the founder of the cookie mobsters. And he has a son, Chip Choclatione. And Chip is currently an associate at the cookie mobsters. And he has been promised a promotion to become a made man if he can cut down on costs and the way cookies are made and shipped. So, of course, this is a typical network design problem, so we are very excited to help with this and to see if we can help to make Chip a made man in network design by helping to cut down the costs by optimizing the way their network works. All right, so of course, this is an optimization problem, and as usual, we have an objective, and our objective is to redesign this physical cookie network in order to minimize costs. So what type of costs do we have? There are a lot of different costs you can have in a network design problem. For us, right here, we're going to consider 4 different costs. The first one is transportation costs. So this is how much it's going to cost us to ship cookies from a bakery to a distribution center, or from a distribution center to the store. So you can imagine that has to go a longer distance, or if you have so many cookies, you need multiple trucks, that's going to cost more. So we want to take the transportation costs into account. We have the cost of having a DC open. So there might be a fixed cost of just having a DC open in a certain location. It's probably going to cost more to have a DC in the middle of Manhattan than somewhere in the suburbs or some rural area. So there's a cost there. Production costs, so it might cost different amounts to produce different cookies at different bakeries, and the same with labor costs. They might be different across different locations. So we have a bunch of costs, and we want to minimize those costs by making a number of decisions. So the first decision we want to make is which cookies to bake at each bakery. We're also going to decide the shipping path from a bakery to a DC to a store, and which DCs to close, if any. So right now, the Cookie Mobsters have 27 DCs open, but it's possible they only need, say, 22 DCs open. So if we're going to close some of them, which ones can we close, and which ones would minimize the overall cost? And of course, we have our constraints. So we have to meet the demand. People really need their cookies. We have to meet the demand. And we don't want to exceed production or inventory capacity at any site. So every cookie bakery can only make so many cookies in a day. So we have a capacity to how many cookies we can make. And then we have some physical limits of the transportation network, right? You can only send so many cookies from point A to point B on a given day. So those are our constraints. And we're going to put this all together into an optimization problem. So this is the problem formulation in words. We're going to minimize the sum of the costs. So for simplicity here, we are assuming that all of these costs are about the same magnitude and have equal importance. So we're just taking a straight sum of them. But if you have costs that are different magnitudes, or some of them are more important than others, then you might want to put a weighted sum in there. But for now, we're just taking a straight sum. So we're going to minimize all of those costs, subject to our constraints of meeting demand, not exceeding any capacity, and adhering to the physical limits of the transportation network. And hopefully we can help solve this problem to help Chip in his goals to become a true mobster. All right, so here's the math formulation. We're going to go through it piece by piece. So there's a lot of variables, but hopefully we'll be able to explain all of it. So we have a few. Go ahead.
So one thing I'll just add too is with this math formulation, if you're maybe less technical, bear with us for a few slides, and we'll get out of the math in about 4 or 5 slides here.
Yeah, we will. We'll go back to the mobsters. Okay. Okay, good. Okay. So we have a few input parameters. The cost. So we're going to kind of abuse the notation here. We're going to use C to refer to all of different costs, and we have the superscript that says what kind of cost. We have our demand. So they're going to tell us how much demand for each cookie they have at each store. And then we have a physical upper bound that's going to tell us exactly how much capacity we have at each part of the network. And then we have a few decision variables. We're going to have 3 continuous variables. Our production, so at each bakery, how many cookies we're making. And we have a cookie flow, so how many cookies are going from point A to point B. And we're using that variable F to refer to both the flow from the bakeries to the DCs and the DCs to the stores. So all the cookie flow. We're saying these continuous. These are continuous, which means you can make partial cookies. That's just for simplicity, but we can just assume that we can make any amount of cookies. All right, we also have 2 binary variables. Our variable Z, which is going to keep track of whether each DC is open or not. So it's going to be 1 if that DC is open and 0 otherwise. And then we have our X variable, which is keeping track of whether a lane is open. And a lane here is referring to if there is any cookie flow from point A to point B, then that lane between those 2 locations is open. So we're going to keep track of that as well. All right, so given all those input parameters and decision variables, we have our objective function, where, again, we're summing these costs. So the first piece is our transportation cost. We're multiplying that cost so we can assume this cost is per cookie, per unit for each of those lanes that we have open. So we're going to sum up over all of those different lanes that are open, multiply that by the number of cookies that are going in that lane. So transportation costs plus the open DC costs. So summing up over all of those fixed costs for having those DCs open. And then lastly, we have our production labor costs. So how much is the cost to produce each cookie and the labor cost producing each cookie at each bakery. So that's our objective function. We have some constraints. First, we're going to have our physical constraints, which are kind of our capacity constraints. The top one there is our production capacity. If we sum up over all the cookies at each bakery, it has to be less than that production upper bound. And then for the flow constraints, we also have capacity on each lane. So how many cookies we can ship from each point A to point B. Those are the second and third constraints there. And the last one is our inventory capacity. So I say inventory here because if we're going to store cookies at a DC, we have a capacity of how many cookies we can store at that DC, but it also can just be, a DC can only handle so many cookies that it takes in and distribute those out to the stores. So there's some upper bound on how many you can ship to a certain DC before it goes on to the store. All right, we got our flow constraints. So the first one, all of these are just kind of making sure what we make is what we send out, what goes into a place is what comes out of it. What goes in must come out, right? So that first one is just saying whatever you're producing has to be equal to whatever flow you're sending out of that bakery into all the DCs. The second one there is saying anything that goes into a DC has to come out of it. And the last one is saying that anything that goes out of a DC has to meet the demand. So here we have this as an equality constraint. We're saying that if you kind of combined all of these, it would just say that everything that you're producing has to be equal to the demand. You can have it as an inequality constraint just by saying that you have to produce at least as much as the demand. But for simplicity here, we're just saying we're meeting the demand exactly. You might want to have a cookie buffer, but we don't have a cookie buffer. All right, and then lastly, these are some indicator constraints that are pretty common in network design and a lot of different integer programs. And they're really just keeping track of the relationships in between the integer variables. So those first two are saying that if there is open lanes into a distribution center, then that distribution center is open. So it's an if and only if. The first one is saying if that DC is open, if there's outflow, then the DC is open. So that Z variable, if that is 0, so that DC is closed on the left-hand side, then that right-hand side also has to be 0, right? Because it has to be less than or equal to 0. So we're saying that DC is closed and there's no inflow into it. And then the second constraint there is saying that if the DC is open, so if that left-hand side is 1, the DC is open, then the right-hand side, the sum of those must also be 1. So if that DC is open, then something is flowing into it, right? So that DC must be, there must be some inflow into it. And then those last two constraints are something we call a big M constraint. And big M constraints appear in a lot of network design problems and also just some integer programs. And we want to choose that value of M so that's sufficiently large so that we get a good relationship between that lane indicator variable and the flow. So for that third line there, we want to choose M large enough so that if X is 1, so if that lane is open, then that number on the left-hand side is so big that it's not a binding constraint, that it doesn't matter. It's not actually forcing a constraint onto that flow variable. So we're just saying it's going to be so large that F has a free upper bound. But if X is 0, left-hand side is 0, that means that the flow is 0. So if that lane is closed, then there's absolutely no flow on it. And then that last constraint there is saying that we want to make sure if there's no flow, then the lane is closed. So if that right-hand side, the sum of the F's is 0, then we're going to force X to also be 0. But if the sum of the F's is anything positive, then there's going to be no constraint on X. All right, so we got our if and only ifs there, and that's a big M constraint. And we're going to put it all together, and we get our optimization formulation. So this is our network design formulation for the Cookie Monsters. And as always, this problem can be modeled and solved in Gurobi. And the solution we get is going to give us which DCs to open, the optimal combination and quantities of which cookies to make at each bakery, the shipping routes of those cookies from the bakeries to DCs to stores, all while meeting the demand and staying within the physical limits of the system. So we can solve this problem. It's a mixed and interlinear program because they're both binary and continuous variables. And it is sometimes the case, not always, that the more binary variables you have, the harder it can be to find an initial point, and it might take longer to solve the problem. So that is not always the case, but in general, if you have a problem that is taking a long time to solve, and you have a lot of binary variables, and you can reduce the number, then reducing the number of binary variables probably can't hurt. All right. So as optimization people, we spend a lot of time formulating the problem and modeling it and solving it in Gurobi. And that is obviously a big piece of things. But Russell and I have talked a lot about how we end up spending a lot of the time, actually, once you get a solution, finding something that's realistic and feasible and really works for the application. And so we're going to talk a little bit about that and what that process looks like, because in practice, solving the problem is usually not as uncomplicated as simply getting a solution.
Yeah, and one thing to add to that too is there's a whole another dimension to this problem that we're not going to cover in the webinar today, which is data collection. And oftentimes we find in these types of projects, there's a fairly large amount of time that's spent with the business collecting the right data, validating it, running it through the model, perhaps doing some iteration, because once you run the model, you then find out that it's exploited some areas where the data is a little wonky, and then doing some iterations there. So those are all actually very big parts of these projects. Get a whole nother talk on that. We're going to talk a little bit more about using the model today. So once you've gone through that, once you have a model which is built, that's giving you results that you validated, how to use it to be dangerous for the business.
Yeah, exactly. And one of the things that we've done is creating these scenarios. So when we take all this business knowledge and the consumer preferences into account, you might have a model and you want to solve it in a few different scenarios based on different outcomes and different possibilities in the future. So we're going to talk about that. So what types of scenarios? There's almost always a baseline scenario, and baseline can mean a few different things. I'm going to talk a little bit on the next slide about what we mean by baseline scenario, but basically the idea is just defining what's happening in the current state. So what's happening right now, and once we have that baseline, then we can optimize from there and show what kind of improvements we can get. Then we have a Greenfield scenario, and Greenfield means that there are basically no constraints. No extra constraints, right? So if there were no business considerations taken into account, what kind of decisions would the model make, ignoring the current state or any like realistic things that can happen. So if we just optimize everything, what do we get? What's optimal? And then there are business scenarios. So if Don and Chip tell us that there are just certain things that are not going to fly because of certain preferences or certain relationships between branches, then we're going to have to take those into account too. So we'll get some business scenarios. All right, so baseline scenario. So what we mean by baseline scenario is creating some extra constraints or using input data in the model that is going to give us exactly what's happening right now. And there are two big reasons why we do this. The first one is to tune and validate the model. So if we can recreate exactly what's happening right now, if we can add a bunch of constraints and say, okay, this is what's happening right now in your model, and we go back to the cookie mobsters and say, we think last year you spent $100 million on shipping cookies throughout your network. And they say that's exactly right. Then we know that we validated the model and that we're modeling their network properly. So that's a big piece of it. And the second part is being able to provide a method to measure the cost savings, to measure our improvement, right? So if we have a baseline for what you're doing now, then we can say when we optimize, we're going to save you this much. That's our improvement. And the goal in this is usually to fix the model variables to match historical behavior. But as a lot of us know, when you have an optimization problem and you have a lot of constraints that are exact, you might not always find a feasible solution. So you can have these kind of soft constraints, and you can say, okay, well, let's say last year in Chicago, we made 95 peanut butter cookies every Wednesday. But you can have kind of a soft constraint and say, well, let's just say that once a week in Chicago, we made between 95 and 100 peanut butter cookies. So you have a range, a little bit of flexibility there so that you're going to get something that's feasible, but close to what actually happened historically. And you can even do kind of like a light baseline, so you can fix not all of the variables, but some of them, say fix which DCs are going to be open, fix which cookies are made at which bakeries, but maybe not the quantities. And that won't overstate the model, it won't kind of overfix it. It will give you something that's close to what happened in the past. All right, so to do our baseline scenario, we have to structure the input data and the constraints to simulate the current state. So we're going to go to Chip. Chip is going to tell us everything that happened last year, where the snickerdoodles were made, what % of biscotti was made in New York, things like this. He has this clipboard there with very serious notes on it. We're going to take all this information and we're going to put it into the model to try to recreate this baseline. So we're going to add a bunch of constraints. And this is an example of kind of what I was talking about, the baseline. So if we have our P hat, which is the actual amount of cookies produced at a given bakery in the last time period, then we can add a constraint to say that the production is going to be equal to what it was last time period plus some epsilon. And then we can add that epsilon into the objective and say, okay, multiply it by some weight and add to the objective, so we want to bring down that epsilon to make it as small as we can.
So one of the things that I always find interesting about creating baseline scenarios is that there's frankly a number of ways to approach that, to figure out how do you do that. And it depends a little bit on what data is available and how the business operates. So, you know, fundamentally, as I think about a baseline, what I'm trying to figure out is how do I create something where I'm using the model to cost out something which is appropriate to modeling how the business operates today. And one of the things you find in there is there's a lot of oftentimes one-off execution decisions that might not line up with the way the model is structured, with the hard constraints in the model, right? So I might have, for some reason, had a one-off shipment from one location to another, or used temporary DC as overflow because I ran out of capacity, or had, used the line 145 hours a week when I had 144-hour capacity in the model, right? So there's a whole bunch of reasons why you may end up having to have some type of soft constraints. And one of the key things is if you're thinking about using the baseline versus an optimized scenario to measure cost savings, what you want to try not to do is give yourself credit for fixing the execution error in your optimized model, right? So that's why sometimes it's important to allow some degree of freedom in a baseline in certain cases, right, to make sure that you're not giving yourself too much credit for the performance, for the solutions that are found in the mid.
Yeah, that's a really good point. All right, so I think I just give an example on the production constraint, but you can add similar constraints for all of the different variables we have in the model. Okay, so once we solve our baseline constraints, or our baseline scenario, we can solve our Greenfield scenario, which means we can solve this optimization problem with no extra constraints. We're just going to say if everything is possible, me and Russell are pictured here, we're going to come up with a solution that gives us a solution, the optimal solution. And we're going to go to Chip, who is very anxious here, based on our recommendations, and we're going to give him these high-level takeaways from the model. So we're going to say, okay, when we solve with absolutely no extra constraints, we are going to tell you that you have to close the main DC in Chicago. It's just not worth it. All the cookies at the store in New York have to be received from the DC in Atlantic City, and all peanut butter cookies have to be made at the bakery in New Jersey. So we're going to go back to Chip and tell him all this information. And of course, that's just not realistic. So this really stressed Chip out so much that he started smoking here. He comes back to us and he says, we can't close the main DC in Chicago. It's our flagship DC. That's crazy. The bakery boss in New Jersey is allergic to peanuts, so we can't make any peanut butter cookies there. And there might be a limit to how many cookies we can ship from Chicago to New York because those branches don't always get along. So this is an example of solving something like a Greenfield scenario with no extra constraints and saying this is exactly what you should do. And then there's the business scenarios, right, where they come back and they say all right, well, that might be optimal, but there are just certain things that we can't do. So we have to add constraints in the model to make the solution something that's actually pragmatic and works with historically how the business has been run. All right, so we, of course, go back. We are very obliging, and we force some things, right? We can say, okay, the Chicago DC will definitely stay open. We're going to add a constraint in there to make that DC open. We're going to make sure that no peanut butter cookies are made in New Jersey, and we can limit the number of cookies that go from Chicago to New York. So let's say we all decide, we agree that, all right, only 10% of Chicago baked cookies are going to go to New York. So we can add constraints for all of that. All right, so another thing that's common in network design problems is to add a new location. So let's say Don comes to Chip. Chip is still very overwhelmed, stressed now. He took up drinking. And Don says, all right, we need to build a new DC, and you have to tell me where. So you can imagine this is a lot of pressure. Chip still really wants to become a made man, so he has to please his father. So you might think this is very intimidating, right? Because there are infinite locations where you can place a new DC. But in general, usually there are actually a finite number of options. Just because you might want to place something just outside a major city, or you already have DCs in place and you don't want to put too close to each other. And there might be new stores that are coming up in a different part of the country or a different part of the world, and you want a DC close to them. So in general, you can narrow it down to a few options. And in our case, we can narrow it down to 2 options, Naples and Sicily. And this is because consumer preferences. So the boss, Don, has 2 favorite bakery managers, and he wants to promote one of them by also putting them in charge of a DC. So Chip has to decide between Cupcake Frank Napolitano and Joey Sugar Marciano. And he wants to do this very objectively so there is no drama within the family or bakeries. So we have to help him decide which one is going to get this DC. And we are all on edge because this could go wrong if we choose the wrong one. All right, so we're going to come back with some analysis on which DC is the right one to open. So you can imagine we can take those 2 DC options and add each new DC and then figure out if we were to add one in Naples, how much does that cost? And if we add one in Sicily, how much does that cost? And we can do a cost comparison. And this is a typical kind of, comparison you can look at across all the different scenarios in the end. Baseline, Greenfield, business scenarios, and then adding new DCs, which one is going to be optimal. So here, for choosing new DC, it's obvious, it's a clear-cut solution, so we'll end up getting something. We should place one in Naples, but it might not always be clear-cut.
Yeah, and this is actually, I think, one of the really important ways to use a network model once it's developed, right? So, oftentimes the more academic view of a model is I build it, it gives me an optimal solution, that's the best thing you can do. But the reality is just oftentimes real business constraints that come into play on why somebody might not choose an optimal solution. So just hypothetically, not necessarily an example we're talking here, but let's say I had 2 solutions, one that cost $100 million and opened up 5 DCs, and one that had cost $101 million but opened up 3 DCs, right? Because maybe I'm spending more on transportation costs but have fewer fixed facilities. A company might come back and say, I'm more willing to invest a little bit more because I know there's some overhead costs of managing additional facilities that's hard to capture in the model, right? Or I believe that transportation rates are going to go up slower than my labor rates are going to go up, and therefore, as I think about what that network looks like, in the long term, it's going to, actually change over time. And now you could say, well, we really should have modeled that with time periods to, look at year 1, year 2, year 3, and that's something you could also do. But, I think one of the real values of once you build a model is not just getting out the optimal solution, but being able to, 1, do all these different scenarios with it, and then 2, once you've found an optimal solution for a model, how robust is that? How close is the second most optimal solution to your optimal solution for a given scenario? So there's all these different types of things you can do once the model is built, and I think that is the true power where using this type of math for the modeling comes from.
Yeah. All right. Okay, so another thing to consider is seasonality. So here in this example, we have it at the end, but usually this is something you consider at the beginning. And because it's Halloween, we all got dressed up. I really like my ghost costume for Russell. But in real life, right here, we're considering Halloween, but usually there might be peak seasons or non-peak seasons, so that demand can be higher, say during the summer or during the winter, and you might have different demands at different times. So there might be a higher demand for some products and lower for others in different seasons. And so you might want to have different models because the optimal network might be different in each season. And in our example, you can imagine during Halloween that there is a very high demand for pumpkin cookies, and the demand for other types of cookies might go down. So during Halloween, we might want to model or use the same model but have different demands. So we might get a different optimal network design. So in our case, if we model this, we might get some kind of solution that says that when there's a higher demand for pumpkin cookies, it turns out that the optimal network design is different. You might want to make pumpkin cookies in Chicago during Halloween, but when it's not Halloween, you're going to want to make them in New York. And the same with cookies sold in Atlantic City come from New York, and maybe those ratios are different when it's not Halloween. And DCs might be different too. Which DCs are open might change. All right, So those are all the types of scenarios that we're going to consider. We helped Chip successfully become a made man in network design because we gave him a solution that saved them a ton of money and took everything into account. So it's a happy family.
So Nicole's talked a little bit about this example problem, and what we wanted to do is talk about, what are some of the common types of things that come out of these network design problems that are important, right? So, if I'm the business and I'm thinking about somebody who's coming to me with this model, right, and the model's coming back and saying, open these DCs, right? Some of the questions that get asked, or we typically get asked when we're in these types of exercises, first of all, is how robust is the solution, right? Is it sensitive to changes in demand, right? All these models are based on the idea that over time I have some demand forecast, right? And you can see inaccuracies in the demand forecast, both in terms of your seasonality, right? So for whatever reason, maybe my Halloween sales this year didn't hit expectations. What does that mean? Or I'm going to get a high year. I'm actually going to do really well. Am I going to have space on my distribution network to actually get all the product out? Do I need to look at having like 3PL overflow or other things built in there? If so, does that change the way my network should be built? Or looking at the forecast in the longer term, right? Hey, 5 years, the business could have a high side scenario or a low side scenario, depending on how growth materializes. We're oftentimes going to want to know which costs have the biggest impact on the solution, right? Is it more sensitive to transportation, or is it more sensitive to my labor rates? Because that might dictate some of the decisions I'd make between picking, the most optimal scenario or maybe the second best scenario. There's temporal considerations. I think I just talked about some of those, but then also people might ask the question, great, I want to open up these 3 DCs. When should I open each one, right? Do I do it all now? Do I want to open up one next year, one the year after, one the year after that? So you can use this type of modeling by introducing time periods to help look through some of those things. And then typically when we do this type of work, we get a lot of questions that are adjacent in the supply chain that you should be prepared to answer, right? So some of them are ones you could answer from this type of modeling, right? What size distribution center should I need, right? You can help at least glean or look at that by at least having some options in the model and the different costs and seeing if the model will select one versus the other, putting some capacity on there. There's other types of questions that are harder to answer. For example, will my payload be affected in the model? Or, and sometimes what you want to do in the model is, it's hard to say like what an individual truck payload might be, but there are certain types of constraints you can put into the model that are not necessarily related to payload. So for example, we have an XIJ variable. You may put something there which represents if I can ship from a DC to, say, a customer. We've built models before where they said, or to a store, where they said, I really only want to store serviced from one DC. I don't want to service it from 2 DCs. The reason is because my payload's going to go down and potentially my service level too, because I'm going to have, a lot more trucks going around. So, those XIJ variables that are in there are things that you might not need if you don't have that constraint, right? You can actually formulate what we did without them. But for certain types of constraints, having those lane variables are important, but it's at the trade-off of runtime. So that's one thing to consider. Other types of common challenges you run into in this type of work is, for large networks or, tricky constraints, or when many variables come into play, this is just sort of a common challenge or thing to work through with mixed integer programming is your long times can get long, your run times can get long, you run into memory problems. So we want to always make sure we're giving a few tricks that can help. The first one is, can you reduce the dimensionality of the problem, right? So, if have every product, can I look one level higher on the product hierarchy, right? Or if I have a lot of customers or stores that I'm servicing, can I group those by, a zip 3 or some other type of geographic area to reduce just how many variables are in the model? You can always look at reformulating the model too. So for example, we have these XIJ variables in there right now. There's reasons why a number of constraints that happen around it. You might want to use them, but we don't necessarily need them, right? So, you know, can I remove those, right? Can I reduce the size of that big M constraint, the M, to be as small as possible so there's a tighter constraint? Or are there other types of business decisions I can go and cement in the model, right? If I know that I always have to send product through a certain DC for a certain type of product, I can fix that flow, and I can then reduce the decisions of the variable, decisions the models to make, or if the DC has to remain open, fix it open to reduce the number of the decisions the model's making. The other thing that's always helpful is having a warm start to the model, so giving it an initial solution to work with. It doesn't have to be a good solution, right? You can have it say, the feasible solution is the one where I've opened up every DC possible, right? Assuming you don't have other constraints that it violates, right? But even giving it a bad solution will oftentimes help the model, especially if it's spending a long time trying to find that first feasible solution. And, you know, one of the tricks here is, you know, hey, if you have the same set of code and you've just changed some of the data that's going into the model, you can always just rerun Gurobi with like the new objective function if you change your objective function. And if you just run it before that, it will automatically give you a warm start. That said, it's oftentimes a good practice to have some type of warm start in your model. So, you know, this is what we do. You know, we help companies with model development. We do business process consulting, and we also do coaching for analytics teams. So if this is new to you and you guys run into trouble, we're always here to help.